Okay, let's get started. So today I'm going to talk about this paper that I'm doing for a seminar class. It's not my paper. It's by a group at Cambridge, and it's about it's about using machine learning and NLP to classify non-native accents into what country they're from. And the name of the paper is Automatic Characterization of Pronunciation of Non-Native English Speakers Using Phone Distance Features. So let's get started. So the task that they do is there's two tasks. The first task is to predict the speaker's mother tongue. So let's say you got a bunch of speech from somebody from France or somebody from China, and you want to classify what country they're from or what their mother tongue is using a bunch of accident speech in English. And then the second task is to predict or to score the pronunciation on how good the pronunciation is. Are they near native or are they barely intelligible? And the data that you use is spontaneous speech, which is important because in this kind of tasks, there's two ways of doing it. The most straightforward way is to get them to read a bunch of text that you give them, and this is easier for the computer to recognize because you know what they're gonna say. But it's less informative because it's as opposed to spontaneous speech where they just say something out of the blue without you knowing what they're gonna say, and that's gives off more linguistic signals than if you give them a fixed text to say. But it's harder for computers because you don't know what they're gonna say. So there's been a bunch of previous work on this topic. A lot of previous work have looked at a bunch of features like phonemic features and prosodic features. So a non-native English speaker would make a bunch of errors, like phoneme mispronunciation. If you pronounce a d as t, then you get a weird accent, or if you delete or substitute phonemes, if you get like the length of the vowel wrong, the vowel's in the wrong position, your tongue's in the wrong position, those are phonemic features. And there's also going to be prosodic features. So the stress of a word, like English is has stress. Some syllables are stressed and some syllables are unstressed. If you say unstressed, that will be incorrect. And then rhythm and intonation. And for machine learning system to extract these features, they used features like vowel duration would be one to figure out if you're saying the right vowel, or a bunch of spectral features. Phonemes are also useful for distinguishing which vowel that you're saying, and stuff like rate of speech, F0 contour. This is stuff that indicate your pitch or your intonation. And then a particularly interesting one is GOP, which I'll cover later. Right. So GOP is an interesting one. It's not covered in this work, but it's interesting because it's how do I clear this? Right. So it's interesting because it's a common way of scoring a pronunciation if you know what the sentence is. So if you know what a sentence is, basically what it does is it estimates the probability of your utterance given the fixed sentence. So if the sentence is so how this works is you first use a system to align the phonemes. So a sentence is the cat sat in a room, and then you say like the dog sat in the room. Then you're going to align each word, like the and then k. You're gonna make an alignment with the with the correct answer, and then you're going to score the likelihood of each phone individually. So in this equation, the numerator would be the probability of your language model producing this acoustic segment for each segment, and then divided by the by all possible segments. So the probability that the k is a k sound versus some other sound, and then you normalize this across. You sum this across all of your phonemes, and then you divide it by the length. So this gives a pretty good scoring system that works for detecting non-native speech. But the problem with this is that it requires you to have a transcript of what you're saying, so the text has to be fixed. It doesn't really work for spontaneous speech, and that's nice. But it's this paper introduces something slightly different, and the idea is if you're a non-native English speaker, then you're going to pronounce the phonemes of English incorrectly. So here we have a vowel chart of English. Like here we have E, which is pretty different from U and A. Those are pretty unlikely to be confused. But then we also have E and E, like seat and sit, which are similar, and a lot of languages don't distinguish them. So if your native language is not English, then you might confuse seat and sit, or you might pronounce both as seat. And the way that we capture this is we can use these as features. So if you can measure the distance between my E and my I sounds, then that's a feature. If my E and my I sounds exactly the same, then I more likely have this type of accent. Whereas if my U and my sound exactly the same, then I'm more likely to have a different type of accent. So there are 47 different phonemes of English, and for each pair of phonemes, we can extract a distance feature. So the 47 choose 2 would be 1081 pairwise phoneme distances. So over here, the middle vowel here is and then we can see that in this speaker the distance between and is pretty small, but then the distance between and between and E is a lot bigger, and then it's not shown here, but then we have like consonants like t would be way out here somewhere, and it's really far from any of the vowels because it's a consonant, but the distance feature is still going to be there, right? So in order to compute these, we're going to have a distribution of all the instances of a phoneme by a given speaker, and to do this, you will have to model this as a distribution. And normally, in speech, you can model the progression of a phoneme as a Gaussian mixture model. So if you extract the MFCC coefficients, and then you aggregate across all of the instances of the vowel, then this gives you a distribution over some high dimensional space, and then you can fit a Gaussian mixture model over it that represents the distribution for every phoneme. And then given two phonemes, you have two phonemes here. You have PI and PJ. We can calculate the KL distribution between the Gaussian mixture models of the two phonemes, and this is just a measure of how similar are the two distributions. So it gives you a distance function between every pair of distributions of Gaussian mixture models. So this is a fairly standard equation that tells you the difference between two distributions, and it's called the KL divergence. And then next we have the JS, the Jensen-Shannon divergence, which is just the average of KL divergence of both ways. So if you know about KL divergence, you know that it's asymmetric. So the KL divergence between P and Q is actually not the same as the KL divergence between Q and P. So to make this actually a distance function, we take the average of both ways, which is JS divergence. And then the third equation here is the KL divergence as applied to Gaussian mixture models. So we have a Gaussian mixture model. PI and PJ are both phonemes, and they have their own GMMs. And then when you apply the definition of JS divergence to GMMs, then you get the equation that looks like this. Okay, so the dataset that they use to train on this is called the Business Language Testing Service, the BULATS. And this test comprises of several spontaneous responses to prompted questions. So they get a bunch of situations that they have to respond with in a few sentences. And this is for a testing service to test how good your English is for a non-native English speaker. And the score range of this is 0 to 30. So 0 being really bad pronunciation and 30 being native pronunciation. And as well, we also have the demographic collected in this testing service. The candidate indicates what the first language is and what country they're from. And in this paper, they also crowdsourced some transcriptions. So they got people to transcribe a bunch of the audio, and this is used for training the ASR system. And here you can see the demographics. They have a lot of Spanish speakers, 4,000. Well, this is just training dataset. So they have a lot of Spanish speakers. They have a bunch of Indian languages, as well as a bunch of European languages as well. So all kinds of languages here. But they also have a lot of languages that are fairly uncommon. So they have some kind of class imbalance here, which might be a problem as we see it later. And they also do a kind of train test split. They use a special. They allocate a bunch of the training examples to train the ASR system, and then there's a system to and then there's a set of examples to train the actual model. That's not ASR, and they actually make sure to keep those separate so that the data is not contaminated. Okay, so here's the procedure that they do to train the whole thing end to end. So first thing they do is they train the ASR given all the speech and the transcripts. So this is a custom ASR model using HTK and SRILM toolkits, which I'm not too familiar with, but basically they said that they tried the standard ASR systems and it didn't work very well because the speakers had such strong accents that it didn't work very well. So they had to train a custom ASR on the accented speech, and that worked somewhat better. And the reason you need to train the ASR is because for the next step you actually need some kind of transcription, so you can align it, which is step number 2. You get this transcription from ASR, and then you get the and then you take the original audio clip and then you align the phone, so you can say this segment from this millisecond to this millisecond timestamp is T sound, and then here is like R sound, and then all of this is done automatically. And then for each speaker you take all of the alignments and then you group them all by phoneme. So it's like here is all of the times where they set some kind of R sound, and and then extract them. Here's all the times that it said some kind of air sound, right? So then now at the end of step 3, you have a bunch of I guess like a set of clips, audio clips for each phoneme, and now you can train a Gaussian mixture model. You train a Gaussian mixture model for each speaker and each phoneme, and for each speaker now you can use the previous equations to compute all 47 choose 2 pairwise phoneme distances, pairwise phone distances, and this gives you just a big feature vector of numbers that you can use for the last step, which is feed it into a deep neural network for classification or regression. And it's like 6 layers, so not terribly deep, and 1200 hidden units each. And so you feed it all into a neural network, and then the last layer is either classification or regression. So let's see how this does. So the baseline features. So they compared with some baselines, which is the features that other people previously used for this task. So stuff like fluency, prosodic measures, vowel frequency, F1, F0, like speech duration, vowel duration, stuff like that. And they actually run this experiment 3 times. Each time they so once using just the baseline features to do the classification, once using just the phone distance features, and the third time using all the features, so both the baseline and the phone distance features. And now let's look at some results. So the first table here is the measures ASR performance, and you can see that so A1 is the worst speakers, and C is near native speakers, so very proficient speakers. And this is each cell is a word error rate when this is the native language and given the level of the speech. So you can see that generally the word error rate goes down as the speaker gets better, which is expected. So A1, the word error rate is a lot higher because the mispronouncing a lot of words, whereas C, the word error is somewhat lower because they got a lot better at speaking English. And yeah, so the next one is a score prediction. So this is when you're trying to predict how well they're speaking English. Are they speaking it very well, or are they speaking it very poorly? And here they use 2 different metrics. First one is PCC, Pearson correlation coefficient, and mean squared error. And both of them are evaluated with respect to the ground truth. Since this is a regression task, these are pretty common error metrics, and they find that the best performing model, so MSE is lower is better, and PCC is higher is better. They found that the best performing model is the baseline plus the phone distance features, and yeah, this I guess makes sense because they're using all the features, and all of the features are kind of important for determining the score of the pronunciation. And then next one is L1 classification. So how well do the models perform on classifying the speaker's native language? And here the accuracy is actually maximized using the phone distance features. So the baseline features do worse, and then the baseline plus the phone distance features actually do worse than just the phone distance features. And then the reason they gave here was that pretty much all of the information was in the phone distance features, and then the baseline features just contained more or less the same information. So then just adding the baseline features actually made things worse because you're adding either features that were not important or features that were already incorporated in your existing phone distance features. So that was interesting. and you can see there's a lot of class imbalance in the dataset. So for high resource languages like Spanish and Hindi and Tamil, which are have a fairly large number of speakers, the classification accuracy is pretty high, like 97.7% for Spanish, whereas for the lower languages, for like much more uncommon languages in the dataset like Oriya and Korean, the classification accuracy is pretty terrible. Like Marathi and Oriya, you get 0% correct, and Marathi speakers often get classified as Hindi, which is understandable because the closely related languages and they sound very similar, but 0% accuracy for Marathi it's not that great. And here you can see a confusion matrix for 3 groups of languages. The top one here is the Romance languages. So Spanish, French, Portuguese, and Italian. Spanish has the highest accuracy, whereas you go down here, Italian only has 2% correct. You get confused with Spanish and French, and you only get it right 2% of the time. And then over here, a similar thing occurs in the Indo-Aryan, so a bunch of languages in northern India. Gujarati is pretty good, but then Marathi you get classified as Hindi the majority of the time. And then last table is Dravidian languages, which is another group of Indian languages that are different from this group of Indian languages, but similar thing occurs here. And this table shows what is this? This is the classification accuracy segregated by the language level. So A1 being the worst, and C2 being the most proficient, and right. So here the best performing model is the phone distance features, and not the combined one. And then the best performing is around here. This is the best. As the highest accuracy is between like moderately good speakers. So this is interesting because you might expect that the worst speakers are probably the easiest to classify because they make the most mistakes, but actually they found that if like beyond a certain point they're speaking so badly that the ASR system just cannot pick up the words correctly, and they cannot do the phone alignment correctly, so then just the system doesn't work as well when your level of speech is too crappy. So that's pretty interesting, and I'm wondering if there's some way of fixing this, because this seems like if you're making a lot of errors, then it should be easier to detect what your native language is, but just not with this system. Yeah, so that's pretty much it for this. So to summarize, this paper introduced a new method of scoring pronunciation and classifying the speaker's L1 using phone distance features. So this is a group of features that weren't really considered before in research, and one advantage of this is it doesn't require transcripts. It can work on spontaneous speech without requiring a transcript of it. And I put ish here because this claim seems like first of all, they actually do use transcripts to train the ASR system. If they try to use the off-the-shelf system like I don't know, like Caldi, then it doesn't work as well because they expect native English speech. It doesn't work very well when you give it accented speech. So it do actually require transcripts to train part of the model, and also I feel that the method of not using transcripts can kind of be applied to any method that does use transcripts. So so what I mean is, if you do have a method that does require transcripts, then you can just run it on an ASR system to get the transcripts. So like that's not really too different from what they're doing here, because what they do is they kind of do require transcripts, but they just run the ASR system on your speech to produce the transcripts, which is not really an innovation. But anyways, so possible improvements and future work. I wonder if it's possible to actually not require transcripts. So this would probably help for the previous table where you're trying to classify people that speak English really poorly, and then you're doing badly because you require it to go through the ASR system. I'm wondering if there's a way to not do this. Would that improve the classification accuracy for really bad English speakers? And secondly, just is there some way to fix the class imbalance issue so that let's say lower resource languages don't just classify it as Hindi and Spanish just because they have less data sets? Like, can you somehow achieve similar accuracy across all the classes? I wonder if that's possible, but they didn't do this in this paper, but that would be interesting directions to try. Yeah, so that's it. Thanks for listening.